Here we're going to look at question 3 from section 2 of the ENGAA specimen paper. So in this question we have a probe which is moving at constant velocity v through space. Then, at a time, the fuel in the probe explodes, separating it into two different parts. So the first part moves at a velocity greater than the initial velocity, still moving forwards, and the second part moves at a velocity less than the initial velocity of the probe, but still in that direction. It's still non-zero. So what the question asks us to do is to consider what happens to the kinetic energy of the probe, of the system, the total energy of the system, and what the total momentum of our system is going to be, what happens to it. So if you'd like to have a go at this question yourself, then please pause the video now, otherwise let's have a go. So let's go ahead and think about each of these things one by one. So the easiest things to think about are probably the total energy and total momentum, for the simple fact that we have conservation laws, that energy and momentum are always conserved in total. So for a whole system, you can never lose energy or momentum, it's going to be in there somewhere. So this just means that they're both going to be the same before and afterwards. Nice and easy, and it's always going to be true. So sometimes, just on a side note, you might be doing some maths and find that energy doesn't seem to be conserved, or it gives you a weird answer, just in a general question, usually an explosion sort of question. And that's usually because in the maths you don't always accommodate for energy of different times. So you may forget a term, kind of accounting for thermal energy, or energy stored in like a fuel source, for example. But momentum should always be conserved. And even though you might miss out energy in your maths, it's still going to be there somewhere. So moving on, we can try and think about the kinetic energy. And to do this, it's probably easiest to try and think about the energy transfers in the system as a whole. So initially in our probe, we can have some different types of energy. So what are these going to be? Well, we're going to have the kinetic energy of our probe, and we're also going to have the energy stored in the fuel, the chemical potential energy of the fuel. So of course we're then going to have this explosion, which is going to release some of this potential energy. So after the explosion, we're going to have this same initial kinetic energy plus whatever the energy from the fuel has become. So this energy hasn't changed at all. The change is going to come in here from the fuel somewhere. So what different types of energy is the fuel going to be turned into? Well, if you were to picture an explosion, then you'd probably imagine a lot of heat, and you'd also probably imagine a lot of shrapnel flying away. And that's because our fuel is going to combust into thermal and kinetic energy. So it's going to release thermal energy, obviously in the form of heat, and then kinetic energy, some of the parts will blow apart, such as these two here. So after the explosion, we're going to have the same initial kinetic energy plus this extra bit here from the fuel. So the kinetic energy of our system is going to increase, with that increase coming from a loss in the potential energy from the fuel. So while the total energy is the same, the different types of energy are being transferred between one another inside the system. Now if we go ahead and compare these with the answers we're given in the question, we'll see that it corresponds to answer G.